So let's start with computing more examples, curvatures of more examples. But now, from the parametric equation of the surfaces, right? So you have phi S actually. So this phi gives the local coordinates on a piece of the surface. So whatever point on the surface that we are interested in, you take a patch around that point and calculate the curvature from this map phi, the coordinate map phi. When we had the surface as a level surface, the orientation was given by the normalized gradient, right? N was del f normalized del f, that is del f over norm of del f. But now, how do you calculate the normal here when you have a parametric form of the surface? So this is the function which gives you the parameters on the surface there. So if you look at the partial derivatives of the function phi at any point, these form a basis for the tangent space at that point, right? If you look at P, so the tangent space to the surface at the point P, so this is a basis for the tangent space. So in other words, any tangent vector you can write as A times phi of u plus B times phi of v. So we are in the two-dimensional case, right? So two-dimensional surfaces in R3. So the normal vector is a vector perpendicular to the tangent plane. So you have two basis vectors here on the tangent plane, two linearly independent vectors, phi u and phi v. So how do you get something which is perpendicular to the plane? You just take the cross product, right? So the normal at any point is therefore given by, this is your usual cross product of vectors, but you want normalized normal, so just divide by the norm of this. So this is going to be the orientation normal vector field, unit normal vector field on the surface at a given point when you have this parametric form of the surface. So when you want to calculate, so this is how you are going to calculate. You are given the map phi, so you can compute the partial derivatives, and from the partial derivatives you can calculate the normal by taking the cross product. So this cross product is going to be non-zero, okay, because these form a base, they are linearly independent, right? cross product of two vectors is going to be 0 only when one is a multiple of the other. The two are linearly dependent. So here they are linearly independent. They are linearly independent by the assumption, right? The gradient is non-zero. So at least one of the partial derivatives is going to be, both the partial derivatives are going to be non-zero in this case. So this is going to be the calculation. So what was the formula for the Gaussian curvature? K at any point is given by where E, F and G are the coefficients of the first fundamental form. So E is phi UU, F is phi UV, G is, because the functions are all smooth, so phi UV and phi VU are going to be the same. So you can write either way here. So this purely involves only the inner product in R3, right? It doesn't involve the second fundamental form, but these L, M and N are going to be in terms of both phi and N here. So L is phi UU dot N. Of course, so if you want, you can, when you take the dot product, you can take the differentiation to the other side if you want. So you can also write it as phi U dot NU and so on, right? Or phi dot NUU, etc. So this N and that N are going to be. So let us put a, right? So this is your, this N is your normalized normal, right? Unit normal. Or we can switch to small EFG. Anyway, okay, doesn't matter. M is the middle square product of the last. So to compute the curvature, therefore, we just have to compute these 6 quantities, right? Take the sphere or even the plane. How do you write? Can you write a plane as a parametric? sphere. So how do you get the parameterization of the sphere? Use the spherical coordinates, right? Cos theta, cos phi. So let us write uv everywhere instead of, so cos u, cos v, cos u, sin v, sin u, right? So u and v belonging to appropriate intervals. You can check, so if you square and add, this square plus this square will give you cos square u, right? And then sin square u. So let us compute. I am not writing the intervals and all that, where u lies and v lies. So you must remember that when you write a parametric equation like this, or a parametric map like this, so this covers only a part of the surface. You don't get the entire surface when you restrict to an open interval, usually, right? So what is phi u? Just differentiate. Now it's all now calculation that you have to do. Phi u, what? Minus sin u cos v minus sin u sin v cos u. So you have to compute all the second partial derivative. So parameterization is not unique, of course. Why not cos u here and sin here, or this and this? Why cos v here and sin v here? Why not the other way? Okay, so it all depends on the interval that you are taking and which part of the surface that is going to cover. So better do the calculations yourself, and also of course check whether what I have written is correct. this and this, what do you get? Cos square minus cos square u cos square v. So this with itself phi u v dot phi u v. So sin square u sin square v that is 0. And then see square of this sin square u cos square v. Here plus minus minus plus la. Oh, minus in na paishna. This is the first term. Okay, the second term is cos square u sin square v with a plus sign. Right? So this comes from this. Is it okay now? Okay, so this is going to be cos square u. So what is happening now? So what do you get therefore? Cos square u. So this is what you get from this. Oh, minus sin square u minus sin square u. That's all. Okay. Yeah. So now you have to calculate the other ones. So first of all you calculate the cross product of phi u and phi v. Oh, I have rubbed off. Cos u cos v. Cos u sin v. Minus cos square u cos v minus cos square u sin v what's that? So n is going to be, so what is the square and add, so what are you going to get? Cos to the 4u plus square of this. Oh, so if you take cos square u, so this is cos square u. Just cos square u, right? Huh. So what is n therefore? So you have to divide by cos u. Assuming that of course cos u is positive. So your domain When you take the square root of this, so mod cos u is what you have to write. So on the domain where cos u is positive, this is going to be minus cos u cos v minus cos u sin v minus sin u. Just so divide this by this. So n by definition is phi u cross phi v divided by of course where cos u is negative you will get the sign changed. Mod cos u will be minus cos u, so this will be plus, this will be plus, this will be plus. Oh, so we have to now calculate Lm and n. So L is so you don't have the expression. So you give me. So you have. Fortunately, u is pretty simple in this case. So what does this tell me? Phi u you already have. So you have calculated n now. So give me what this is. Okay, so what is this? The square of this. Right? This one is going to be 1, huh? Okay, good. Apron m m equal to 0, very good. What about n? What you get for k? So this is going to be cos square u. Look at the cylinder. Cylinder is something important. So what is the cylinder? X square plus y square equal to 1. Oh, did we calculate in that case using the other? I think we forgot about it. But now let's calculate using this thing. So what is the parametric thing now? Cos u sin u equal to 1. This is arbitrary, okay? This should be a lot easier to calculate. Products, there are no products involved, so. So lots of things are zeros, so quite convenient. So what is phi u cross phi v? Cos u sin u, huh? 0. Last one is 0. Cos u, comma sin u, comma 0. Right? Is that what? So normalize, the norm of this is 1 already, so this is also n. So let us write EFG. So what is E? Phi u u, right? Minus cos u minus sin u 0. F is phi v, so it is 0. G phi uv, that is also 0. Phi uu dot n minus 1. Is it minus 1? This dot this. So minus cos square u minus sin square u 0. Phi uv is 0. Right? So this is going to be 0. It's also 0. So, is it okay? So what is k therefore? K is ln minus m square Eg minus f square. So the cylinder has 0 curvature. See, these are numbers, right? EFG are numbers. So what I have written is something absurd, right? What is E? You have to take dot products. It's not a vector. EFG are numbers, right? So what did we write in the beginning today? Phi u dot phi u. That's what E is. EFG are not vectors, they are numbers. Okay. Oh, the sphere also we made, we had written like this, then of course. Then how did you calculate? You don't get a number at all. Phi u is a vector, so it doesn't give you a number. Phi u, the second derivatives come only in LMN, not EFG. So phi u dot phi u is 1. phi u dot phi v is 0. Phi v dot phi v is 1 again. So now the denominator is 1, numerator is 0. But then how did we say in the earlier thing that the denominator is 0? E was some vector, F was some vector, G was some vector. We said 0 by 0 and all that. Okay, so the sphere also, that was that made all the mess, I suppose. Okay, so now this is fine. So the what is it? The cylinder has curvature 0. So in fact, there are two principal curvatures, right? The two-dimensional case. So like this one, like this one, right? The horizontal direction gives you one direction, and that is the y direction and the z direction. These are the principal directions in that case. If your cylinder is like this, right? The axis, z axis. So one of the principal curvatures is 1, the other principal curvature is 0. That's what happens actually. The Gaussian curvature is a product of the principal curvatures. That means for the not Laplacian, what is it? Weingarten map, eigenvalues are 0 and 1. So and the determinant therefore is 1. The mean curvature is half and so on. Okay.